So today we're going to talk about this thing called a function. Okay? A function is a rule that changes a given x value to a y value. And for every x, there is exactly one y. You've seen functions before. The graph y equals x. The graph y equals x squared plus 2x plus 3, or y is equal to x squared. Basic quadratics are functions, right? And straight lines are functions as well. The domain of x is what we call the set of x. We say the set that x can take for a function. You've already been doing that in the last unit. You were finding what values x could be, i.e. the solutions. When we hear about something called the range, we're actually talking about a thing called the y value. What values does y take? So we're actually saying what values that y can take, okay, in a function. You would normally call the x value the domain. You would also call the y value of a function the range. When we're talking about the equation y is equal to f at x, we say that y has to be calculated. So we say that this is the dependent variable. The fact that we always have to pick our x values makes this thing the independent variable. Okay, so we're now going to talk about the concept of a function. Suppose I have the function f of x is equal to x squared minus 3x, right? I want to know this. F of negative 2 and f at x plus h. Now, what I want you to imagine, if I go and put a 2 in here, into this f of x, if I change x to 2 or negative 2, this also becomes negative 2, and so does this. So now, here's our solution. If I have f at negative 2, that equation turns into negative 2 squared minus 3 times negative 2, which is equal to 4 minus, plus 6, which simplifies to 10. So f at negative 2 is equal to 10. Now, what I would like to let you know is that if I have f at negative 2 is 10, this means our y value and our x value have been determined, and we can see what they are. In this case, my x value is 2, negative 2, and my y value is 10 for the point, if I ever wanted to graph that function or that value. Now let's compute f at x plus h. And we're just going to substitute wherever x is, wherever that stuff is, where x was, we're just going to replace it with x plus h minus 3 and x plus h again. So that allows us to expand to x squared plus 2xh plus h squared minus, now we're going to take this negative 3 and apply it to everything inside this bracket. And we're going to get minus 3x minus 3h. And when we simplify, there's not much to simplify. That's it. We're done. There's no like terms, so we're done this problem. So f at x plus h is equal to this. And moving on. Now we're going to go and compute a thing called the domain and range. And this is going to allow us to figure out a whole bunch of things. So now we're going to determine the domain and range for the equation y is equal to 1 over x. Now, remember, I told you that the domain was always talking about what values x can take. Now, if I look at this equation, all we have to do is look at our equation here, and we'll notice that x cannot equal 0 because of this denominator here. Okay, so now, because that is not possible, if I wanted to draw what that looked like on a number line, I'd have the point 0 for x, and then all of the points to the left and to the right of 0 are not touched. So what that would mean is we would say this. The domain of x, now when you see this line here, this means such that. So x, all x's such that you just say x is not equal to 0. And x is actually just a real number. Now, based on what our number line looked like, this is what the interval notation is. And we're done. We've done that before. So literally, this is the final answer for what your domain is. So what this domain tells us is what values of x my equation can take. So for this equation, let's call it equation 1. Basically, the domain is that. Now, because I know the domain is 1, is this, we can also say that the y value, i.e. the range of the y's, are also the same. So you have y such that, well, y can equal 0 because it's 1 over something, but is not ever equal to 0. So y cannot equal 0. And then we can say y belongs to all real numbers. Now, the reason why that is if you think about it, if x becomes really, really negative, 1 over a negative number is still negative, isn't it? And then if x becomes very, very positive, that means 1 over a positive number is still positive. So this means it's all the real numbers that we had in our original number line. So every other point except 0. So our y value, when we set it up as our range, our interval notation is negative infinity to 0, union of 0 to positive infinity, just like before. So the next concept we're going to take a look at is a thing called the vertical line test. The vertical line test says this. So if every vertical line that intersects a graph of an equation does so in exactly at most one point, then the graph is considered a function. So let's say I had a graph that looks like this. Here's the XY line, and then we have a graph that looks like this. Okay. Now, what it's saying is if I have a vertical line and I can move this line all the way across this thing, and it actually just touches the curve at exactly one point each time, then we can say this is a function. And yes, it is a function. Okay, it is a function. Can't even write the word it today. All right, so that is one thing that we could use. So anything like a parabola, anything like a straight line, a straight line that's not vertical can work. Let's go and take a look at this next problem here. Let's say I have a parabola that's laying on its side, okay? And we're using the vertical line test to see if this is a function or not. So now what I'm going to do is I'm going to take my little vertical ruler and I'm going to move it across this thing here. So once I hit this new graph, oh my, oh my goodness. It looks like I just found 2 points that touch this line exactly, this vertical line at exactly 2 points. And I would say that no, this is not a function. It is not a function. Now, it's all because I can take this line and I can move it across here, and my graph will always touch my vertical line at 2 points after a certain point. So this is not a function. And so now we're going to do 2 more problems for the day. No, 3 more problems for the day. And one of them will involve our sign chart from last time. So today you'll be doing problems that are similar to this. So we're going to determine the domain of a function in interval notation. Now, one of the types of functions that you'll see is something like this. Let's say I have f of x is equal to x minus 2 cubed over the square root of x minus 4. Now, the domain is what values of x make this thing possible, right? Now, as an aside, anytime we have a square root function, whatever is underneath here has to be greater than 0. So, therefore, the x minus 4 underneath the square root sign has to be greater than 0 in order to make this not be undefined. So we have to say, we don't want it undefined. We don't want it undefined, right? So because we don't want it undefined, we have to say x minus 4 is greater than 0. Not greater than or equal to, but greater than 0. And so now we're going to take this -4 and move it over to this side. And we don't have to do our chart calculations yet. So we end up with x being greater than 4. So therefore, the domain, i.e. the x values that we can use on this function, are the interval starting at 4, open bracket, going to infinity. Now, if you're not confident doing the interval notation right away, draw your number line. So here's 4. There's my circle, and my points go this way. So now that I have that, I can easily go and create my domain calculation. So now let's do another problem. So the next type of problem that I'm going to introduce you to today is something like this. Let's say I have the function g of x is equal to the square root of something plus the square root of something, right? I'm actually going to let this one be x minus 3, and then this part here be x squared minus 4. And so for this type of problem, underneath the square root signs, we have to identify the fact that we have stuff that is greater than or equal to 0 underneath the root sign. Okay? So now, because of that, we're going to have to work on the stuff that's underneath the root sign. Now, by doing so, you're going to have to say, okay, 4 x minus 3 greater than or equal to 0, you're going to solve. And we're going to do that right now. Okay? And then you're going to take a moment and make sure that you draw your example of the number line with this point. So remember, it's a filled in dot in red, and it goes that way. So now let's discuss what happens to this part here. For x squared minus 4, we got that greater than or equal to 0. Okay? Now, when we go and solve for this, we're literally going to be running through the gamut. Now, because it's a quadratic, we always have to factor. So we have x minus 2 and x plus 2, okay, which is greater than or equal to 0. Now, I'll show you a quick trick. When you have a quadratic like this, right, you can easily figure out what the values are. Okay, so imagine you have the equation y is equal to x squared minus 4. So that's what that would look like. It's a parabola that's shifted down, right? Now, we are looking for all values where x makes the y value, where x minus 4 is greater than 0. So that's all of these points right here, right? That's what happens when y is greater than 0. And when does that happen? It occurs at x equals 2, which comes from here, and x equals negative 2, which comes from right here. And the more important thing that we're going to acknowledge is that our x's are less than or equal to that and greater than or equal to that. So that's what we have for our solution. So we've got, in this case, x is greater than or equal to 2, or x is less than or equal to negative 2. Now that we have that, I'm just going to draw my points on a number line. So here's my first point, here's my second point, and one goes this way, and one goes that way. Okay, so now we got to look for where they overlap. So now let's combine these two graphs and see how all this stuff works. So when we combine those two number lines, we end up with this. We have our 3, we have our 2, and we have our -2. And my -2 goes this way. The +2 goes this way. And my 3 goes this way. All right. So now I just have to look for the thing for where the two graphs overlap. They only overlap at x equals 2. And now, so they only overlap in this section of our work, right? So because they only overlap there, those two are what I have to consider. This can't be used. So I have to look at x. So if I have x is greater than or equal to 2, that means x is greater than or equal to 3 works for both of them. So that means my final answer is going to be the domain is equal to this bit here, which is 3 greater than or equal to infinity. And we're good. We're done. Okay, for this next problem, we've got 5 minus x over x has got to be bigger than or equal to 0. That's what we have to start with, okay? And in doing so, we have to identify the fact that our zeros are the following. 5, and the undefined value is 0. So let's go and check using our favorite thing, the sign chart. So we end up with this sign chart. Now, because we have this sign chart, what happens is we can take a look at this and we go this, and this works perfectly for us. And so our domain, or otherwise known as our solution, is this. The domain starts at an open bracket for 0 and goes up to 5, but because it ends at the actual 5, it's a square bracket, and we're done. Okay, and we're done. So your homework is 15 questions, okay? They are from the booklet on page 55, and we're going for number 3 to 33, and that's odd. And you guys are going to have at least a week to do it. So you can work on that while you're gone. Right? In class today for about 15 to 20 minutes. Then you can start studying for your test. And then we'll do the second lesson. It'll take us about 10-15 minutes. You know what? I changed my mind. Do 10 of these. Do only 10 of those questions.